We are the paradoxical ape. Bipedal, naked, large-brained, long the master of fire, tools, and language, but still trying to understand ourselves. Aware that death is inevitable, yet filled with optimism. We grow up slowly. We hand down knowledge. We empathize and deceive. We shape the future from our shared understanding of the past. CARTA brings together experts from diverse disciplines to exchange insights on who we are and how we got here. An exploration made possible by the generosity of humans like you.
Hi, everybody. So I actually had a much longer title for this talk, but CARTA asked me to cut it because obviously it wouldn't fit on the poster, which I think is a nice metaphor for what we're doing here and kind of the broader goal of CARTA, which is to take these huge, broad, complex topics and get rid of all the fluff, all the poor attempts at alliteration, and really get at the core of what they mean for human origins. So this is what I'm going to do now for the next 18 minutes, talking about interbirth intervals. So IBIs, interbirth intervals, refer to the length of time between a female's subsequent surviving offspring, so birth spacing. And together with other aspects of development and life stages, they are studied within the evolutionary framework of life history theory, which looks at how organisms allocate energy, which is a limited resource, to the competing purposes of maintenance, so keeping yourself alive and healthy, growth, and reproduction. Specifically for interbirth intervals, the competing demands are the trade-offs between current reproduction and future reproduction. So when do you stop investing in your current offspring and start planning for the next one? And from an evolution perspective, this is one of the most critical life history aspects for a female because it determines her overall lifetime reproductive success, which is the fodder of natural selection and therefore evolution. Now, every single aspect of reproduction for a female mammal is extremely costly. So usually female mammals are either pregnant, lactating, or cycling. They just don't have enough energy to do more than one thing at the same time. And when it comes to interbirth intervals and determining their length, we can think of two main constraints, two indeterminants on how long they're going to be. One of them is a female's own physiology, so the female's energetic requirements. And in fact, what we see is after a female has given birth, she will enter what's called postpartum amenorrhea. So this is a period of suppressed ovulation, there's no cycling, there's no possibility of conceiving again. So this length of time in which a female is in postpartum amenorrhea gives us kind of the minimum physiological IBI that a female can sustain. But there's another individual involved in this equation, and that's the infant. So obviously you don't want to curtail investment in that infant too early, you don't want it to die, and so the timing of weaning is going to give us the minimum interbirth interval length for infant survival. As I mentioned, lactation is very energetically costly, and so usually weaning, lactation, and postpartum amenorrhea all correlate. So fairly straightforward, right? No. So this is a very simple diagram looking at all the factors that lead to the length of postpartum amenorrhea in humans. You can see centrally prominent there, energy availability, so energy expenditure and energy availability. What I'm going to do now is not try and go over all of these, but focus on the ones that are most important and do this from a comparative perspective. So let's broaden the lens a little bit to the other great apes. And in general, what we see is that humans and the other apes have the relatively slow life histories that we associate with large-bodied animals. So slow development, small litters, usually only one offspring at a time, long lifespans. And we can think of this life history as being on a spectrum where on the one end you have animals like chimpanzees, pictured here, that invest in quality. So these are K-selected species that have small, few infants very rarely. So chimpanzees, for example, here, once every 5 years. And then on the other end of the spectrum, you have species like oysters that have 500 million offspring a year. So clearly it's on a spectrum, and great apes tend to end on the K side of the spectrum. Now in this table, that I'm going to show you a little bit of the time because there's a lot of data, I have collected data from a bunch of different publications on key life history traits in the apes. And the first thing you might notice is that they're not sorted as you would usually see them, and that's because instead of genetic proximity, I have them sorted by adult female body size, which within closely related species is one of the main determinants of life history. So here on the top, you have the main kind of average weight that is usually used in the literature, but because these are from a lot of different wild populations, there's different means that are reported at different sites, and so in the brackets, I actually have the range of means that I found in the literature. I also included gibbons as kind of the outliers, both in terms of genetic proximity to humans and also in terms of their body size, as they're the smallest of the apes. So humans here in kilos, about 46 kilos, so about 100 pounds, slot in between orangutans and gorillas. Now, when we look at pregnancy length, everything seems to kind of follow from the female's body size, right? Humans at about 270 days don't look very different from orangutans. Gorillas are maybe the weird ones. You can ask me about that later. But once we start looking at infant age at weaning, things start to get a little suspicious. So 2.8 years is the reported average for humans. That is much lower than orangutans, also much lower than chimpanzees. For bonobos, there's not a lot of good published data, but it's assumed that it's about the same as chimpanzees. And then when we look at interbirth intervals, that's really why this is a CARTA topic, right? So instead of what you would expect, about 5.5 for chimpanzees, 7.6 for orangutans, humans have an interbirth interval of less than 4 years. And that is the most similar to that of gibbons, who have a body size that's a tenth that of humans. How is this possible? What is happening here? So we're going to dive a little bit deeper into both humans and chimpanzees, and I'm using chimpanzees as the main comparison for the great apes because they're the most closely related to us, together with bonobos, but also because orangutans have made the evolutionary decision to just live life in the slow lane, and they have the longest IBIs, not just of all the apes, not just of all mammals, but as far as I know, of all animals. So they are not a very good comparison. We can talk about that later as well. So let's start with humans. So for the other great apes, those are values from wild populations. For humans, they are the values based on natural fertility, hunter-gathering populations. So natural fertility means they don't use chemical contraceptives, they don't affect their reproduction in any way. And so the idea is these values approximate the evolutionary norm for our species. There was a recent analysis of over 800,000 interbirth intervals from 44 industrialist countries by Sadir and Ponser, and Herman Ponser is actually a CARTA member as well. And they found that in these populations, IBIs were actually shorter. So the range was 2.3 to 3.5 years, and the modal value, so the most common value, was just around 2 years. So how are human females capable of this? Is this some adapted, physiological, evolved adaptation that they can do, some tweak to their physiology that allows them to pop out babies this rapidly? Let's take a second look at chimpanzees. So again, in the wild, the IBI is about 5.5 years, a range of 5 to 7 years. But there have been some really interesting studies looking at the chemical composition of urine and of feces. Yes, primatology is a glamorous field. And what they found was that in females, the energetic burden of lactation actually ended at around 2 years. But then their postpartum amenorrhea lasted for about 3 to 4 years. And so what Melissa Marie Thompson and colleagues concluded is that the birth rates in chimpanzees are not really limited by the physiological effects of infant suckling or even the daily energy costs of milk production, but by the ability of mothers to extract enough energy from their environment to regain physical condition after a prolonged period of high expenditure, such as after pregnancy and lactation. And so this observed variation that we see in the wild likely reflects differences in access to high-quality food. And some evidence for this is that higher-ranking females and females that live in areas with better foraging do tend to have shorter IBIs. Also, we have data from captive chimpanzees where mean IBIs are much shorter, about 1 to 2 years shorter than in the wild, and as low as 1.7 years. And even in the wild, there have been a couple of instances of recorded interbirth intervals as short as 2 years. And in bonobos, closely related species, not as well researched, one documented interbirth interval of just 1 year between infants. So, okay, maybe this is something that humans and their closest living relatives share, some kind of very strong physiological flexibility that allows them to range with these kind of extreme interbirth intervals. Let's see if that's the case. And this is where I get to introduce you to my study subjects, which are olive baboons. I study them in Kenya at the Was a Near Baboon Project, which was established in 1984 by Dr. Shirley Strum, a UCSD faculty member and also a CARTA member. And what's been really interesting there is that we had the opportunity to observe a natural experiment on the effects of better diet on reproduction. So that red fruit that juvenile is eating is a fruit of prickly pear cactus, Opuntia stricta. This is an extremely, extremely invasive plant species. It is actually native to the American Southeast. You might be familiar with it. And it has spread at our study site and has become an important part of these baboons' diet. And it's high in calories, mostly in the form of sugar, and water. So the animals that have been eating it, especially the females, are in really excellent body condition. So here's a satellite image of our study site. Up here in Doldol, this is the origin site of the spread of Opuntia. And one of the study troops that we were following, Ngela, ranged pretty close to the origin site. And so they had been eating Opuntia for quite a while. But all the way over here, 20 kilometers away, there's a second study troop. It's great having multiple study troops. And they hadn't quite eaten Opuntia yet. And so we were able to track the kind of effect of Opuntia on their reproductive intervals in real time. So here is 2014, where Ngela, in the darker red, has been feeding on Opuntia for quite a while at this point, whereas Namu is only starting to have it in their range and starting to introduce it in their diet. And you can see that in 2014, interbirth intervals between Ngela and Namu were markedly different, with Ngela having markedly lower, shorter interbirth intervals. And then what you see over the course of the next 3 years is that interbirth intervals in Ngela stay consistent. They keep eating Opuntia. But in Namu, they steadily decrease until they converge on the interbirth intervals that we saw in Ngela. And just to put this into context, I have this table that shows what I'm calling control groups of baboons, and then baboons in groups that have increased caloric intake and the interbirth intervals for the two. So in the wild, again, at a range of different sites, we see an interbirth interval of about 1.5 years to 2. And then in captivity, again, you see this effect of better provisioning, better diets, and interbirth intervals in captive baboons are only about 1.2 years. So the effects of Opuntia in Namu, the troop that had not been eating Opuntia for long, you can see that their interbirth intervals are within the range of wild baboons. In Ngela, the animals that had been eating it for a while, you can see that they're now below what you would usually see in the wild. But this wasn't the first time that Shirley had seen better diets influence female reproduction. She had actually observed the development of a raiding, crop raiding tradition in baboons, where they would go and steal food from the local farms. And what she documented was that in the non-raiders, you had interbirth intervals that were within the range of wild baboons, but the raiders had such short interbirth intervals that had only been seen in captivity. So it seems like this flexible physiology in response to high-quality foods and more energy availability is not something unique to humans. It's not something unique to apes. It's not something unique to primates. So since interbirth intervals are the outcome of these competing energetic demands on females, we can really understand the variation in their length as reflecting variation in maternal energy availability. So to shorten them, as we've seen, one thing you can do is increase the supply of energy, so more, better quality foods. And I will point out that this does not just mean to the mother. The availability of good weaning foods, things that can supplement an infant's diet as it's transitioning out of being nursed, can also decrease this burden on females. And in fact, that's one thing we think might be happening with Opuntia. It's a fairly easy food to forage on, even for juveniles, especially the discards are very widely available. But a second thing you can do is decrease the energetic cost of reproduction. And this is where you really get from females in species sometimes having better quality food and being able to reduce their IBIs to what humans are doing, which is making it the norm. So how do you decrease the energetic cost of reproduction? That's where other individuals have to step in. So allomaternal caregiving refers to care provided to the infant by individuals other than the mother. And across animals, this can refer to grooming, caring, and even sometimes feeding. And we know that in primate species, it correlates with lower interbirth intervals. So this little dot right here. And as a side note, that 1 year interbirth intervals that was observed in bonobos, in the report that was describing it, they mentioned kind of casually, the older offspring was frequently cared for by an adult male of the group. So I read that and I was like, aha, there we go. That's what allowed that female to have such a short interbirth interval. Of course, I don't know if that's the truth, but it's possible. Now, an extreme form of allomaternal caregiving is called cooperative breeding. So this is much more extensive care that is provided to the infants by non-breeding members of the group. And across mammals, as you can see here, cooperative breeders have shorter IBIs and produce litters rather than single offspring. Now, in primates, it's pretty rare, but there is this glamorous group of South American monkeys called the callitrichids with these beautiful coats, and they are cooperative breeders. They have short IBIs. You know it's short when you're measuring it in days. And they also regularly give birth to twins, which you can see on top of what's probably not their mother, but probably actually one of the alloparental caregivers. In fact, when they're in captivity, they usually give birth to triplets, and they only have 2 nipples, and so the third one has to be hand-raised by the humans. So their reproduction is really kind of pushed to the max. So what about in humans? Well, at this point, it's pretty much widely accepted and acknowledged that cooperative breeding has played a crucial role in the evolution of our species. And not just in terms of our reproduction, but also in terms of the evolution of some of those traits that we think of as what is making us human. So for example, our prosocial tendencies. If you're interested in this, Sarah Bleffer Hardy has this fantastic book, Mothers and Others. She's also a CARTA member, and I highly recommend reading it. So who's providing this provisioning? Well, it could be anybody. Fathers, this male provisioning might go pretty far back in our hominin origins. Older siblings, there's some interesting cross-cultural ethnographic and ethnological data on the role of older siblings in maybe providing food, but definitely babysitting for younger ones. And then possibly most famously, grandmothers. So Kristen Hawkes here in the audience, also a CARTA member, has suggested that the whole reason, or the main reason we have these long postmenopausal non-reproductive stages as women is that we're actively supporting the reproduction of the next generation. So why us? Why us and not other apes? Why not other primates? Well, the suggestion or the idea is that this is, together with larger brains, larger bodies, smaller jaws, smaller guts, part of a suite of traits that evolved in response to a dietary shift to food that was higher quality, nutrient-dense, but a difficult-to-acquire food resource. So with that in mind, when could that maybe have happened in the history of our species and the evolutionary history of our species? Now, unfortunately, demographic traits don't fossilize, but we can use proxies. So we can use things like body mass increase, brain size increase, and the pace of development. So here's a graph from Robson and Wood, and you can see that really we don't see that increase in brain size and body size until those little green boxes that are Homo ergaster and Homo erectus. So it's really unlikely that shorter interbirth intervals appeared until we have the evolution of a Homo erectus and Homo ergaster about 1.6 or 1.5 million years ago. And in fact, it's been argued that these shorter IBIs may have been necessary for these Homo erectus females to support these greater costs of birthing and raising these large-bodied, large-brained babies. But in order to do so, they required enlisting the help of other group members. So from a comparative perspective, yes, human interbirth intervals are shorter than expected based on comparisons with other apes. This is likely due to a decrease of the energetic cost of reproduction for females. And so one way we do this is by more energy in. So more, better food. We have a seasonally appropriate spread right there, not just for the mothers, but also weaning foods for infants. But really the key that humans have unlocked and the secret to our really, really fast, consistently fast interbirth intervals is that women are not doing it alone, right? There's the sharing of the energetic burden of child rearing. And so to conclude, rather than an evolved physiological mechanism, these higher quality diets and this allomaternal caregiving have created a socio-ecological niche that allows women to have shorter IBIs. And then I want to make just one broader point before I let you go to the next talk, is that phylogenetic comparisons tell us how we are different, which traits are ancestral, which traits are derived. But it's really by expanding our lens and investigating convergent evolution that we can understand why we are different. So what those evolutionary pressures are, what those selective pressures are that have led to the evolution of our unique traits.